Hi, it's good to see you again. So this time I will present my own work on compiler testing. Can I use this? Yeah, on compiler testing, okay? The title is Skeletal Program Enumeration for Rigorous Compiler Testing. So compiler are very important and they are also very complex. So according to the data, this data from the year of 2015, and we can see that the code base of GCC is almost as large as the code base of Linux kernels. And in terms of LLVM's code base, we can see that it involves more than 4 million of C++ code. So they are very complex. And what we are doing is that we want to test the compiler. And it is not an easy job because the compilers are very complex. And the most interesting problem in compiler testing is about input generation. That is, we want to generate interesting programs which can find some issues in compilers. So the state-of-the-art approach first is about program generation. For example, Sysmith, it is a random C program generator. And then the second category is about program mutation. It's about the EMI technique. And it just randomly inserts or deletes the statements in the original C program. So the two kinds of approaches share something in common. The first property is that they are all opportunistic. So they just do randomly generation or mutation on the C program. Well, the second property is that they favor large and complex programs in order to find the bugs in compilers. So here is where we are. We just propose an idea of program enumeration to test the compilers. So our work is based on the observation that most of the interesting testing programs, that is bug triggering programs, are usually very small. And even if the program can be large, and finally it could be reduced to a very small piece of code. And according to this large-scale empirical study, and we noticed that on average, each bug triggering program contains about 30 lines of code, which is fairly small. So based on this observation, we have the vision. That is, we want to test the compilers using only small programs. But rather than being opportunistic, we want to be exhaustive because the search space is bounded. So for example, if we can enumerate the program up to a bounded size, and then we are able to verify the correctness of the compiler up to that bounded size. So this is our vision. In order to realize that, it will take two steps. First, give you a contextual grammar, you need to generate a token sequence, a set of token sequences. For example, there is something like identifier is equal to identifier plus identifier. This is the first step. Well, the second step is that given a token sequence, and say, for example, here, and I told you that if there are two variables and how many unique programs are there. And our approach focuses on the second step, that is, give you a token sequence, we will enumerate all the possible and unique programs for compiler testing. So here is the informal problem formulation. We call it skeleton program enumeration. Well, skeleton here corresponds to a token sequence. We cannot generate a program by ourselves, but we take existing small program as the seed program, and then we converted this program into a skeleton. So basically, what we have in the skeleton is that we replace every occurrence of the identifier here as a whole. And also we know, say, in this example, we have two variables. So we just exhaustively fill these two variables into this host and enumerate a set of programs and then use this enumerated program to test the compiler. So the next big question is, what is the intuition behind this SPE technique? So we can explain it using this very small example. So from the example, we can see that all of the three programs share a same skeleton. And for the first program, we have two variables A and B, and we notice that the variable A has never been initialized, and it has been used on line 3. And when processed by a compiler, the compiler may generate an uninitialized variable warning for this particular program. And for this program, now, the value of A has been assigned to 0, And we know that the branch will always be evaluated to false. So this line is a dead code. So for this particular example, the compiler will trigger optimization phases like constant folding and dead code elimination. And again, in the third program, now the value of b is always 1, so this condition is always true, so this line will always be executed. So after doing constant folding, and we know that there are some common sub-expressions, and a compiler may trigger another optimization path like common sub-expression elimination. So from this simple example, we can see that even though we have a same skeleton, but by filling it with different variables, we are able to exploit different variable dependencies in this code and trigger different compiler optimization paths. And we can use this insight to test the compiler. So next, I will show you a few real-world bugs that we found in different compilers. First is about a miscompilation in GCC's compiler. So the code is fairly small and fairly simple. I have two variables here, a and b, and here I explicitly declare b as an alias of a using GNU extension. So now a and b refer to the same memory location. And the program here is fairly simple. I have two pointers p and q, which point to a and b respectively, and then I assign the value 1 and 2 to this memory location. And we know that after the execution of these 8 lines, both the value of both a and b and also these 2 pointers should be 2. So this program is adopted from an existing GCC's regression test suite. So in the original test program, it returns values of b, and when compiled with GCC, it correctly generates the executable, which returns the value of 2, which is correct. And during our enumeration, we find a variant which returns the value of a, and we hit a bug here because now the program will incorrectly return the value of 1. So we report this bug to the GCC developers, and we got very positive feedback from the developers. It says that it really seems to be a run code bug, and it started a very long time ago with this revision. And this revision concerns with GCC 4.4, which is a release almost about 8 years ago. And this developer summarizing the problem of this example. That is, the GNU alias analysis cannot handle the GNU. The alias is declared using GNU extensions. So the next example concerns with a crash in GCC. So again, the program is also very simple, and the original program was adopted from GCC's regression test suite, and the original program is like this. So we don't need to understand the semantics, but the program is used to test the trinary operations. And then in our enumeration, we find a new instance, which we just replaced the occurrence of E with D here, and nothing has changed. And we notice that E and D are syntactically identical. So the enumerator program should also be syntactically valid. But unfortunately, it crashes compiler. It triggers a constant folding bug in the compiler optimization, in the GCC's constant folding path. So this crash has been marked as release blocking bug, which is the most severe bug in GCC's development criterion, which means that if the developers are unable to fix this bug, they are not able to release a new version of GCC. So this bug concerns with a crash of clan. It crashes at -01 if we compile it without optimization, and the clan can correctly compile this code. So the problem concerns with some internal optimization passes which computes the invariant of this loop. So this is a COMSOL front-end crash. It's just a single line of code, and it triggers an assertion failure because originally COMSOL won't check the completeness of this type declaration before the initialization. So after seeing this example, and we'd like to talk about the challenge in our work. So again, we have a C program, we have a skeleton, and we want to generate a set of programs exhaustively. So there is a challenge here. That is, there are a lot of duplicates if we enumerate it in a naive way. So we call this alpha equivalence programs. So for each of the program, it can be simply characterized as a vector. For example, this program has 6 holes, and each hole can be filled with A and B, so this is a vector. And the program P1 can also be represented as a vector. And so for these two vectors, we know that we can see that it's alpha equivalent because there is a one-to-one map from this vector to this vector. So they are redundant. They are uninteresting because they exploit the same usage pattern, variable usage patterns. So we want to get rid of that. So the technical contribution here is that we propose an efficient combinatorial enumeration algorithm, which we can enumerate alpha non-equivalent programs. We will never, for example, if we have P enumerated, we will never consider P1, but we will generate P2. So in order to do that, we formulate it as a set partition problem, because again, we can see every program as a vector. So a set partition problem can be described as this. Give you a set of n elements, say 6 elements here. I want to partition this 6 element into, say in this example, 2 subsets. So the first subset concerns with variable A, in this case because I have only 2 variables, and then the second subset concerns with the variable B. So the subset partition problem is a well-known combinatorial problem, and it has existing algorithm can solve that. The number of unique set partitions is called the Stirling number of the second type. And for P1, the subset configuration is like this, and we can easily see that both of them are identical because the subset name does not matter. So we use the existing combinatorial algorithm to compute the set partition problem. If we do it naively, as we can see here, we have 6 holes and 2 choices for each hole. We will generate 64 variants. And using the combinatorial algorithm, we need only to consider 61 alpha non-equivalent programs. So the most challenging part in our work is that in the real-world programs, we have additional scope information. For example, in this code, the last 3 holes concerns with a local scope of the while loop, which means that these holes can be assigned with additional local variables. So the scope information makes this problem unique. It's unlike any existing combinatorial set partition problems. So to work with this new set partition problem, and we propose a new combinatorial algorithm to solve that. This is the key technical challenge in our work. Okay, then let's talk about the experiments. So the experiments, we are interested in 2 kinds of evaluations. First is about the size reduction, while second is about the bug hunting capabilities. In terms of size reduction, we take GCC's original regression test suite as an example, and we can process about 18K files. And if we enumerate the test suite naively, we will encounter this amount of variants. And if we enumerate using our SPE technique, we will only consider this amount of alpha non-equivalent programs. So to sum up, we achieve about 6 orders of size reduction. In order to help you understand better about the size reduction, say if we can process each of the variant in 1 second, and naively it takes about 50K years to process all this amount of variants, which is overwhelmingly large. And using the SPE technique, we can exhaustively process all of these variants within 1 month. The second kind of evaluation is about the bug hunting capabilities. So for C compilers, in 6 months of time, we have found about more than 400 bugs. Most of them are crashes, and about 5% of the bugs concerns with the miscompilations. And occasionally, we can also find some cases on the performance issues in GCC. So our idea is general. We can use this idea to test the other compilers. We can also use this to test the scalar compilers. So my supervisor actually met Martin at some conference, and Martin says, well, your technique seems to be promising, and can you use that to test the scalar compilers? And when he came back, he said to me that, okay, let's try this. So we try our technique on two scalar compilers. One is a standard scalar compiler, while the other is the Naughty compiler. In 3 weeks, so in 3 weeks' time, we are able to find about 40 crashes in both of the scalar compilers. So in terms of the ComCert compiler, in another 3 weeks' time, we are able to find about 30 bugs in its front end. Most of them are front-end crashes. So the story continues. We continue our effort to test the compilers using our technique. Currently, we work closely with the LA Fox on testing their new path manager. So this is a screenshot of my mailbox. So we are using our technique to help testing the latest LVN and CLAM. So to conclude, to test the compiler, we had the insight. That is, we can use the programming enumeration to test the compilers. We work only with small programs, but we exhaustively generate all the variants of the existing programs. And we propose an efficient and unique combinatorial algorithm for solving the SB problem. Recall that we have the challenge of handling the scope information in programs. And lastly, we have encouraging empirical result. So that concludes my talk, and thank you very much. And I'm happy to take questions.
Questions?
Yep. I was wondering, you using the scope information to reduce the search space, did you consider something similar with the type information as well, or do you do that already?
Yes, we have actually in our implementation, we have 2 versions. The first version, we discard the type information. The second version, we consider the type information. So introducing the type information does not increase the complexity of our approach, because different types, for example, double and integer, can be considered separately. That is, we enumerate all the variants with respect to the integer. And we also enumerate all the variants with respect to the double or float. And then we compute the Cartesian product of these 2 sets and to generate the final program. That's it.
I also have a question. So one of your assumptions seems to be that the names of identifiers don't really matter because you just look for alpha renamings. So I know that in JavaScript, some engines only apply optimizations if the code size is below some threshold. And to determine the code size, the length of comments, and I think also the length of identifier names is for some reason taken into account, which means the names do matter. So did you see any similar behavior in C compilers or maybe Scala compilers?
In our early days applying EMI, we counted some cases with this variable length problem, which can trigger different kinds of compiler crashes. But when I was doing this kind of work, I have never encountered this case, because our work is built on the assumption that every program will be finally normalized as some standard intermediate representation. And on this intermediate representation, the name doesn't matter. It's just the A, B, C, D, E, F, G, yeah. Mm-hmm. So, but there can be bug converting the program to this intermediate program. But yeah, currently we are not considering that. Yeah.
Very interesting work. So I was wondering about the possible usage for manage the language compiler, like just-in-time compilers. So like Java. So in that case, actually, the compiler usually would be invoked in runtime. You have to really run the code with some input. If you change the code with the input, the program may not be able to run correctly. So what do you can you comment on that?
Yes. So our technique does not guarantee anything. We does not guarantee that the program is runnable. So, but we can use the technique to find the JIT problems. The only thing that you do is that you just find the runnable variants in the enumeration set, and then use that to test the JavaScript engine. And the situation is very similar here, because in C we are able to find the crashes. We are also able to find the run code bugs. But as you see from our experimental result, we can only in our over all the bugs that we found, we have only 5% of miscompilations, which corresponds to the runnable variants. So the portion of runnable variants in the enumerated set is very small. Yeah, but in principle we can do that, but I'm afraid it will be challenge. Yeah.
How do you select the programs that eventually become the skeletons? How do you select the programs that eventually become the skeletons that are then enumerated for testing? Did that make sense?
Would you?
Yes.
Oh, we take existing programs. For example, if we want to test C programs, we just take all the programs from GCC's regression test suite, original test suite. If we want to test the scalar, just take the test, find all the programs on the test folder, and yes, we do not generate program. Yeah.
All right. If there are no more, wouldn't have been. Do you have time? Sure.
So can you say again how you know the expected behavior of the program? It should compile, but what if it compiles and gets the wrong output, or it was supposed to trigger an optimization and the optimization wasn't triggered?
That is a good question. So we cannot guarantee that every program can compile. We can only guarantee that every program is syntactically valid if your input program is valid. So in order to test the wrong code bug, we use differential testing. For C program, we feed the enumerated program to different compilers and compare the output of the different compilers. But there's another problem in C compilers because C programs have undefined behavior. So we need additional tools to rule out those bad cases, and then use those good cases to report and reduce. So that's why we have found a fairly small amount of miscompilations, because ruling out the undefined behavior is very challenging.
So for the undefined behavior, do you compute a set of possible answers by using temporary variables to choose the? Do you enumerate all the possible answers by disambiguating the program and then check that the set's equal?
Yes.
Thanks.
All right. So yeah, let's say thank you to Qirun and to the other speakers of the session.